All right, guys, this is our last section of this crazy semester. We're going to do 5.5, which is substitution rule, or some people call it U substitution. We're going to continue talking about integrating or finding antiderivatives. But if you remember in the past sections, we've been limited to certain rules. And we've said that there's no such thing as product rule, there's no such thing as quotient rule, and there is no such thing as chain rule, right? Until now. And so we have what we call a substitution rule, or use substitution, if we have a problem, an integration problem that looks something like this, where even if I were to take that radical and change it into a rational exponent and make it a 1/2 power, it would still be to me a product rule and a chain rule, and really no way of simplifying it to make it look any different than that. And so we're a little bit stuck until now. And so what we're going to do on this type of problem is we're going to take that inside stuff, that 1 plus x squared, just like it was in the above part up here, that 1 plus x squared, and we're going to call it something a little more simple. We're going to call it u. And then we're going to take the derivative of u with respect to x. So the derivative of u with respect to x, well, the derivative of 1 is 0, the derivative of x squared is 2x. And then what I'm going to do is I'm going to multiply both sides by dx. That crosses off, cancels out the dx on this side, and then I have a dx on this side. And so du is really 2x dx. And so then what we're going to do is we're going to take our original problem, and instead of writing it the way it was, isn't it okay if I take that 2x and bring it to the back? Right? Multiplication is commutative, and so I can put the 2x in the front, or I can put the 2x in the back, and it would be the same thing. So then if you look at my problem, if I take this out and call it u, isn't it now the square root of u? Right? It's the integral of the square root of u. And if you notice that the 2x dx happens to be my exact du. And so what that allows us to do is it allows us to rewrite my original problem in terms of u's instead of x's, but it also ends up turning into a problem that we can integrate now, because now it's really just the integral of u to the 1/2. I have all the same variable, I have u's all the way through, I've substituted in all my pieces properly where I didn't have anything extra or anything missing, and now I have an integration problem that hopefully we can solve now with our power rule. So adding 1 to the exponent and dividing by that new exponent, you end up getting the antiderivative of u to the 3/2 times 2/3 plus c, right? Remember that constant of integration? But our answer, we don't want our answer in terms of u, we really want our answer in terms of x's. And so we're going to take back out this u, and what did we call u to begin with? Well, didn't we call u the 1 plus x squared? And so I'm going to take out the u, and I'm going to back substitute and get a final answer of 2/3 times, remember that u, which was 1 plus x squared, to the 3/2 power plus c. So now I can actually integrate this problem that really looked like a product rule and a chain rule by using use substitution. Okay, so a lot of times, again, this happens when we have a chain rule looking piece where we have an inside function and an outside function. And we would take that inside function, whatever it is, call it u, make sure that we have, though, the derivative of u still in place so that my integral turns into one variable with all the pieces that I need. Okay, I'll do example number 1a with you in this video, and then we'll do ones that get a little more complicated or fun as we go through. Look at example number 1a with me. To me, this looks like if I didn't have this u substitution rule, we would have to FOIL this out twice and distribute a 2x. Now, you can do it, but if we can find a u and a du that replaces all of my pieces perfectly, well, then I can integrate it in terms of u instead, and then just back substitute like I did up above. And so in this problem, I'm going to look for my inside. And so I'm going to call this x squared plus 1 my u. And so that means the derivative would be 2x, right? The derivative of u with respect to x, du over dx would be 2x. I'm going to multiply both sides by dx. And so that gives me a du of 2x dx. Now let's rewrite the problem then, taking out my x pieces and seeing if I can substitute them in for my u pieces. And so I have an x squared plus 1 squared. And instead of calling it an x squared plus 1, can I really just call that a u squared? And then this 2x dx happens to be my du, so I should be able to take out my x squared plus 1, call it a u, so now I have u squared. And then the rest of my pieces, my 2x dx, ends up turning into my du, which is perfect, because now I have all of my pieces substituted in for u's. I don't have anything extra, I don't have anything missing, and now I have an integral that says u squared. And I can integrate u squared with respect to u because they have the same variable. Using my power rule, I can add 1 to the exponent, divide by that new exponent. Make sure you add your constant of integration because we're doing that indefinite integral. And then don't leave your answer in terms of u's because really we want the integral in terms of x's. We want the antiderivative in terms of x's. So now we just have to back substitute. So now take out your u, back substitute in what we called u in the first place, which was the x squared plus 1. And so now we have the antiderivative in terms of x of x squared plus 1, that quantity cubed, over 3 plus c, using our substitution rule.